All right, welcome. Today, we are going on a kind of scientific detective story. We're going to travel back in time, peel back the layers on more than 200 years of discovery, all to answer a question that sounds super simple, but, as you'll see, is anything but.
So what does an atom really look like? I bet an image just popped into your head, right? And that image, it isn't totally wrong, but it's kind of like jumping to the last chapter of a book. The real story is full of these amazing insights, totally shocking experiments, and ideas that literally change the world.
Yeah, this one. We've all seen it a million times. You've got this tiny little nucleus in the middle, and then electrons zipping around it like planets orbiting the sun. It's a nice, clean picture. The only problem? It's really not how it works. So to understand why, we've got to rewind all the way back to the beginning.
Okay, so our story really kicks off with the very first scientific theory of the atom. And it was all built on this one simple but really powerful idea that if you keep cutting something up, you'll eventually hit a piece that you just can't cut anymore. So back in 1808, a guy named John Dalton made this idea official. He actually brought back this ancient Greek concept of atomos, which literally means uncuttable. He pictured the atom as just a solid, perfectly round, featureless sphere. Like a super, super tiny billiard ball. That was our starting point. But spoiler alert, that perfect little sphere was about to get cracked wide open. Yeah, that indivisible model, it didn't stick around for very long. And the key to breaking it, the thing that changed everything, came from a pretty surprising place: electricity. Okay, so fast forward to the late 1800s. Scientists like J.J. Thomson are messing around with these things called cathode ray tubes. They're basically glass tubes with most of the air sucked out. When they crank up the voltage, this mysterious glowing ray shoots across the tube. And here's the cool part. By using magnets, Thomson could bend the ray, and that proved it was made of tiny, negatively charged particles. He had discovered the electron. And just like that, the indivisible atom wasn't. It had smaller pieces inside. This was a huge deal. It forced the first major revision to the model of the atom. So out goes Dalton's simple, solid sphere. And in comes J.J. Thomson's idea, which people called the plum pudding model. The new idea was a sphere of sort of spread out positive stuff with these little negative electrons stuck inside it, kind of like plums in a pudding. It all balanced out to be neutral.
Thomson's model made a lot of sense at the time, but it was about to get completely blown to pieces by one of the most famous experiments in the entire history of physics. Seriously, this is where our little detective story takes a wild, completely unexpected turn. So, a scientist named Ernest Rutherford, who actually used to be one of Thomson's students, came up with a test for this plum pudding idea. His plan was to fire these tiny, positively charged things called alpha particles, think of them as tiny bullets, at an incredibly thin sheet of gold foil. I mean, this foil was just a few hundred atoms thick. And all around it, he placed this screen that would light up with a little flash every time an alpha particle hit it. So let's think about this. Based on that plum pudding model, what would you expect to happen, right? If the positive charge in those gold atoms is all spread out and weak like a thin fog, it shouldn't be strong enough to do much to these heavy, fast-moving alpha particles. Yeah, the prediction was pretty clear. Those little alpha particles should just zip right on through. I mean, maybe they'd get nudged off course just a tiny bit, but that's it. Rutherford himself said it was like firing a cannonball at a piece of tissue paper. You just don't expect it to come flying back at you. Okay, so Rutherford and his team get the experiment running, and they start counting all those little flashes on the screen. And what they saw, well, Rutherford later called it the most incredible event he'd ever witnessed in his life. Just as they predicted, most of the particles sailed straight through. No big deal. And a few of them were bent off course a little bit. Again, expected. But then came the absolute shocker. A very, very small number of particles were deflected at massive angles, and some of them actually bounced almost straight back. We're talking about maybe 1 in 20,000 particles doing this. It was just unbelievable. That's when Rutherford made his famous comparison. It was as if you fired a 15-inch cannon shell at a piece of tissue paper, and it came back and hit you. There was just no way around it. Something inside that atom had to be incredibly tiny, super dense, and positively charged. And with that, the plum pudding model was toast. It was completely gone. The only way to explain these results was if all the positive charge and almost all the mass of an atom were packed into this impossibly tiny little dot at the center, the nucleus.
And that meant the atom was, well, mostly empty space. And that right there is how we got to that familiar solar system picture.
But, and there's always a but in science, right? This new solar system model had a major, major problem. A fatal flaw, really. One that the physics of the day just couldn't explain. In fact, according to the rules of physics back then, this new atom shouldn't exist for even a split second.
Here's the problem. According to classical physics, an electron whipping around a nucleus is a charged particle that's constantly changing direction. That means it should be constantly giving off energy, like a little radio transmitter. And as it loses energy, it should spiral closer and closer to the nucleus until, wham, it crashes and the atom is destroyed. But obviously, atoms are stable. The chair you're sitting on isn't collapsing into nothing. So what gives? This is where a Danish physicist named Niels Bohr steps in 1913, with a really radical idea. He basically said, what if the old rules of physics just don't apply down here at the atomic level? He proposed that electrons couldn't just orbit anywhere they wanted. They were stuck in specific fixed energy levels, kind of like planets being locked into specific orbits or rungs on a ladder. And when they're in one of these special orbits, they just don't lose energy. It was a crazy idea, but it introduced this brand new, super important concept called quantization to the atom. Now, Bohr's model was brilliant. It was a clever patch that finally explained why atoms don't just collapse. But that's all it was, a patch on an old way of thinking. The next big leap, the one that gets us to our modern picture, required something huge, throwing out the old rulebook completely and just embracing how unbelievably weird the quantum world really is. And that next jump came from Werner Heisenberg. You've probably heard of his famous uncertainty principle. What it says is that there's a fundamental limit to what we can ever know about a particle, like an electron. The more precisely you know where it is, the less precisely you can know where it's going, and vice versa. This isn't because our tools are bad. It's a fundamental rule of the universe. And it means the whole idea of a neat, tidy, predictable orbit for an electron is impossible. So this just changes the entire game. We have to throw out Bohr's neat little circular path and replace it with something called an orbital. And an orbital is not a path. It's not a racetrack for the electron. It's a three-dimensional region of space, a map of probability. It doesn't tell you where the electron is. It only tells you where you are most likely to find it if you go looking. We had to give up certainty for probability. So, the modern picture of an electron isn't a tiny dot at all. It's more like a fuzzy probability cloud that surrounds the nucleus. And the cloud is thicker and denser in the areas where you have a higher chance of finding the electron, and it gets thinner and fades away where the chances are lower. It's a strange, blurry, uncertain picture, but it's the most accurate one we've ever had.
So let's just quickly recap this whole wild journey. We started with Dalton's simple, solid billiard ball. Then Thomson came along and cracked it open, finding the electron inside. After that, Rutherford's experiment revealed the tiny, dense nucleus sitting in a whole lot of empty space. Bohr then came and locked those electrons into specific, stable energy levels. And finally, quantum mechanics took over and smeared those neat orbits into these fuzzy clouds of probability.
And all of this leaves us with one last, kind of mind-bending question to chew on. If the atoms that make up you, me, and everything in this room are more than 99.9% empty space, then why does anything feel solid at all?